So, welcome to part 4 of this lesson on population. And this is going to be about the contemporary slowdown in global population growth. So, we've seen that over most of history, world population has been growing according to a hyperbola. And in the last part of this lesson, we saw that it's actually quite easy to explain that. We only need a couple of simple assumptions and then we're pretty much done. It falls out of the equations that p dot is proportional to p squared, hence a hyperbola. But what's not so easy is to explain why it has stopped following a hyperbola, why it has started to slow down and seems to be, as the UN estimates suggest, stabilizing on a population of about 11 billion by the end of this century. So we're going to look at a few theories that try to explain this fact. And we'll start with Kremer's idea. So Kremer attributes it to changing incomes, and specifically the idea that in richer societies, people tend to have fewer children. So in traditional societies, children are needed to work on the farm, to earn money for the family. And they're also a kind of insurance policy for your old age. But in richer societies, that isn't the case. Children are more a luxury than a necessity. And so people tend to have fewer of them. And so this tendency towards having fewer children is what he suggests causes population to slow down. So he suggests that we need to rewrite his basic equation. We saw that from his model, we got that the rate of change of population was equal to beta g times p squared. So beta and g were a couple of constants, g this research productivity, and we have this relationship p dot proportional to p squared, which gives our hyperbolic growth. Well, he's suggesting we need to modify that. So this should become p dot equals r brackets y. This is a constant multiplier factor that depends upon y, the income per capita, times beta gp squared, same as before. And it's this ry that changes. As people get richer, this factor r decreases. And specifically, he suggests that it may look something like this. So there's r of y plotted against y, the income per capita. So richer societies have a higher value of y. And so he'd say that when y is equal to y star, remember that's by that he means the minimum allowable income, the minimum that people need to survive. At that point, that r is 0. That's a 0 line. So at this point, r is 0. So when people have only the bare minimum they need to survive, they can't grow their population. They can't have children to grow their population, though they can just about replace their population. So here ry is 0, so p dot is 0. So population remains steady at that value. It can't increase if y is at y star. And if y is less than y star, then r is negative, because this means people have less than they need to survive, so they're actually starving. So population we would expect to decrease, and r is negative. And so a negative here, negative value for ry means that p dot will be negative, so p will decrease. On the other hand, if y is above y star, then people have extra income and they can afford to grow their families and population can increase. So ry will be positive and p dot will be positive, and the population will be going up. But then the key issue is that he suggests that when it gets to a certain point, though, it's no longer true that r tends to increase with y. It turns over, and above a certain level of income, a certain degree of wealth and prosperity, people start to have fewer children again. There's children becoming a luxury. and it declines down to some value. And so it's this decrease in RY beyond a certain level, so that when the world becomes rich enough, that's when the population will start to turn over and RY is decreasing, the rate of population growth will slow down and maybe come to zero. It depends on what RY does. So various possibilities are that RY can tend to a constant. R of Y is as Y tends to infinity. Let's put that in a different place. So as Y tends to infinity, RY can tend to a constant, it can tend towards zero, or it could tend towards a negative constant. You know, it might actually come down here, something like that, become negative. If RY tends to a positive constant, then population increases without limit. Population can keep going up because RY is always positive. It's coming down to a constant, but it's still positive. So P increases without limit, but avoids a singularity. If RY tends to zero, then P tends to a limit. But in infinite time. So it's asymptotic towards a limiting value. It eventually stabilizes, but it takes a long time to get there. But you could get as near as damn it in a reasonable time. And if RY tends towards a negative value, then P also tends to a limit, but this time in a finite time. P tends to a limit in a finite time, that should say. And the United Nations population data and population projections suggest that we're looking at one or other of these scenarios. It certainly is tending towards some kind of limit. It doesn't look like it's going to keep increasing forever, but whether it's going to reach and stabilize on a particular limit, or whether it will just cruise gently towards that limit in infinite time, we can't really say. But it's one or other of those. So that chart then is the key to Kremer's explanation for why population is now slowing down. If we assume this shape for RY in this equation, then we predict quite naturally a population slowdown. The precise details depending on precisely how RY behaves. Then Korotayev and co. offer another explanation in terms of the growth of literacy. So for them, literacy is a proxy for human capital or education. So they notice in particular that female education is particularly associated with decline in birth rates, lower family sizes. When women are more educated, they tend to have fewer children. So they suggest that the growth of literacy is responsible for suppressing population growth. And so they build a model of equations that captures this effect, which I'll just write up. Okay, so here are their equations. Before we had P dot equals A S P, where A is a constant, S is economic surplus, P is of course population. But now they multiply by this 1 minus L, where L is the literacy fraction, the fraction of the population that is literate. And so it can increase up to a maximum of 100% or 1. So when L is 1, that's a maximum possible literacy, and at that point 1 minus L will be 0, so P dot will be 0. So as literacy reaches 100%, it stops population from growing and will cause population to plateau at some level. For economic surplus, they have the same equation as before, And but they also now introduce an equation to suggest how literacy grows. So they suggest that literacy grows logistically towards its maximum value of 1. So that's the L into 1 minus L. We can see that as L reaches 1, L dot will stop growing. It will stabilize at its maximum value of 1. And but the rate at which it gets there depends on a constant C, but also on economic surplus. So if there's a larger economic surplus, the literacy will grow more quickly towards its maximum value. So, and a higher economic surplus means, you know, more money to spend on education and achieving a literate population. And then to analyze these equations, we can develop a relationship between L and P to find out how literacy should change with population. We can do that by looking at L dot divided by P dot, where L dot is, of course, you know, just means dL by dt, and P dot just means dP by dt. And then we can kind of cancel the dt's on top and bottom. You know, we know that that kind of works. These things do behave like fractions, even though that's not mathematically rigorous. It works like that, so it can be shown rigorously that that works. And we're only theoretical historians, we're not pure mathematicians, so, you know, we're not going to be purist about that. So we can just cancel these. We know that this becomes dl by dp. And that is going then to be equal to, well, L dot is given by this, CSL into 1 minus L, and P dot is there, ASP into 1 minus L. And then quite a lot of this cancels, the S's and the 1 minus L's, so we get C over A into L over P. So our basic equation is dL by dP equals C over A times L over P. C over A is just a constant. And we can solve this by standard techniques for solving differential equations, which we saw in the mathematics module. So we can take the L from there onto this side, and the dP from there up onto this side, which will then give us dL over L equals C over A into dP over P. And then we just integrate both sides, and this will give us on here log L, because we should know that the integral of 1 over L is log L from the mathematics module. And on this side we'll have C over A times the log of P, because again it's 1 over P, integrated with respect to P will be just log P, plus a constant, say K. And then we can take logarithms of both sides. So, sorry, take anti-logarithms of both sides. So log L becomes just L, and this becomes P, log P becomes P, but it's multiplied by C over A. Well, by our laws of indices, that's becoming P to the C over A. And this will become E to the K multiplied by it. So when we take the anti-logarithms, addition turns into multiplication, so that's there. Or we can just represent E to the K by some other constant, which I'll put as lambda. So we find that literacy depends on population raised to some power C over A. So L depends on P as a power law. And we should remember from the mathematics module that we can study power laws with log-log plots, because on a log-log plot, a power law should come out as a straight line. In fact, that's also obvious from this stage, because the log of L is related to the log of P by the standard formula for a straight line. You know, this is like y equals mx plus c. So that's the C over A is the slope of the line, that's x, that's y, and plus the constant, the y-intercept. So anyway, what Korotayev and co do is they do a log-log plot of log L against log P, for the literacy fraction going from 0.1 to 1, and log of p, well, we can write from 1 billion to 10 billion, so that's a logarithm, an order of magnitude there. And what they find, because they can get data on the literacy, calculations of literacy over time, people have prepared such data series, and of course we have the, let's just write that a bit better, that's 10 on the scale, and people of course we have the population, as we've used that a lot, and what they find is indeed there is a straight line relationship on a log-log plot of literacy against population. So in other words, their model, this seems to work, it seems to make sense, and it implies clearly that population will slow down as literacy reaches its maximum value. So it clearly explains why there's going to be a slowdown. And what they do is, because they can't solve these equations analytically, get a formula for P and L out of them because they're a bit too complicated for that, they solve them computationally by an iterative method, putting in some starting values for P, S and L, and then assuming constants and adjusting the constants to get it to fit the data and iterate the model forward, so step by step, using these equations. And what they find is that you get a hyperbolic growth that then turns over, and with suitable values of A, B and C you can get it to fit the our timeline, so that it turns over round about 1970. So that is P against T. And the goodness of fit, is again very high, up in the 99%. The only issue that one might raise with this, though, is that the turnover is very sharp when you do this, and it seems to be sharper than we actually see in the population statistics and projections. That it takes a while to bend round, whereas this kind of rather abruptly comes to a halt. But nevertheless, it's with just one extra simple assumption, it's very effective at explaining why there is a turnover. And our next explanation comes from Sergei Kapitsa and uses the behavior of the arc cotangent function, the inverse cotangent function. Sergei Kapitsa is another Russian kind of theoretical historian from an earlier generation. He was kind of a Russian Carl Sagan type figure. And his explanation for this is based on him noticing that the arc cotangent function kind of behaves in the way that we want. It's hyperbolic for part of its range, and then it turns over and tends towards a stagnant or plateau value. And specifically, where we had for the hyperbolic model that P is equal to C over T0 minus T, he suggests what we actually need is an equation like this. P equals C over tau, where C and tau are constants, times the arc cotangent of T0, singularity time, minus T time over tau, again this same constant. And he says if we do that, the result we get looks like this. If we choose suitable values for C, tau and T0, we will get a curve that looks hyperbolic most of the way and then turns over. And this matches what we've seen. There's the hyperbolic phase, and then this is what's happening now as populations tending towards a stable value of about 11 billion by 2100. and the specific values that we need to make that to work is that C is 163 times 10 to the 9, tau is about 45 years if time is measured in years, and T0 he used 1995. So I call that a singularity, but the point about this is that with the arc cotangent we don't get a singularity. It's looking hyperbolic, it's looking like it's going towards a singularity, but then it turns over. That's how arc cot behaves. So this is all very well, but the question is, where do we get this from? This equation is, we would say, phenomenological. We haven't got an explanation for why that is. It describes it, it works, but why should it be that? Well, one thing we can do is if we differentiate this, so we can sort of get a better feel for what's going on. Let's just differentiate this first, our original hyperbolic equation. We should remember that if we differentiate that p dot, it becomes c over t0 minus t squared. And if we differentiate this equation, and for this we need to know what the differential of arc cotangent is. It's not something we're going to work out from first principles, but just look up in a book. But what it comes to, if we differentiate that, we will come to c over t0 minus t squared plus tau squared. And that's the reason for writing it in this particular way, having not just a constant there, but c over tau and t0 minus t over tau. Then if we write it like that, then it comes to this. Because now we can compare these two and see that the difference in this equation, the only difference is that we've got a plus tau squared on the bottom here. Otherwise it's the same. It's got t0 minus t squared there and there. But here we add a tau squared. And it's adding this tau squared that prevents this from becoming infinite. Because when t reaches t0, making that 0, here we're dividing by 0, getting an infinity. But here, where that's 0, but we still got tau squared. This is a constant, so we still got tau squared on the bottom. So the bottom is still finite. So this doesn't become infinite. And so p dot here doesn't, become vertical. It's still got a slight slope to it, and then it, as t0 minus t, as t goes beyond t0, so t0 minus t would be negative, because t is greater than t0 now, but because it's squared, it's symmetrical. T being above t0 is gives the same value when t is below t0 by the same amount. So in fact this curve will be symmetrical about t0. And so just as it started very flat and then became hyperbolic, so the hyperbola turns back into something flat as t0 minus t squared starts increasing again. So we've kind of got a sort of better feel then for kind of what's going on, that we've got an expression like this rather than that, but we still don't really know what the explanation for this is. Where does this tau come from then? Why should we add it on the bottom line? And Kapitsa's answer is that it's we see it's 45 years, and he kind of notices, well, that's about the same sort of time as the human lifetime, or maybe it's the human working lifetime, something like that. So he suggests it's something to do with the human lifetime and maybe human reproductive capacities, that it's maybe that's the time that we're supporting a family or something like that. But I've sort of read through his explanation a few times, and it's very hand wavy. There isn't really a clear argument there. It is very much like I presented. It's sort of something to do with that. It's something like that. But precisely why and how that works and why it comes into this formula in this way is not at all clear. What we could say though is that when we studied population, we didn't actually start with this formula for P dot. We didn't have an explicit formula for P dot in terms of time. We actually started with the formula P dot proportional to P squared. And we produced an argument why that should be the case. Why should the rate of change of population be proportional to the square of the population? And but having established that, then we know that the solution is that and that. So, you know, we might want to do the same thing here. We won't sort of write why or explain why that formula occurs. We'll explain why something is true about P dot that implies this solution, and specifically, this would arise if we had that P dot is proportional to the sine squared of some constant times P, A times P. So if P dot is proportional to the sine squared of AP, then the solution is P equals arc cotangent. But the problem is that, you know, no one has explained that. So, you know, why should P be proportional to the sine squared of AP? Doesn't seem very likely. How would a sine get in there? So, you know, we haven't got an answer to that yet, so there's a challenge for you. Then another argument is in terms of finiteness, the effects of finiteness. So things are developing in a finite world. So it's pointed out that according to the theory of critical transitions, such as the transition from ice to water, we discussed critical transitions in the mathematics module, according to the theory, at the critical point, there should be patches of ice on all scales, and there's no average size of patch. Patches can be arbitrarily large, and they can be of any size up to infinity, and so there should not be a defined average size of patch. It diverges, we say, it tends towards infinity, the average, because although they're very rare, they're so large, the very large ones, that they drag the average up to, well, infinitely high values. So that's a theory, but in reality, that can't happen, because in the laboratory, you know, we study this in a beaker. And so you can't have arbitrarily large ice patches. They're limited by the size of the beaker. And so the theory breaks down. And so similarly, world population is growing on a finite planet. So it has to break down, even though it can, according to the theory, tend towards infinity. On a finite planet, there's just not enough resources to build that many bodies. So we just are going to be capped by the finiteness of our environment. And so that is why the behavior is breaking down. The theory is correct, but it's simply the finiteness of the planet that prevents the theory applying in reality. Well, you know, this is very true. And it's really pretty obvious. And it's, you know, it certainly explains it, but it doesn't really seem to get us very far. It would be nice if we had some more kind of theoretical way of expressing that. But, you know, but maybe that's all it is just a finiteness effect. Another finiteness effect is that we saw that population doesn't actually follow the hyperbola. The hyperbola is just the envelope of the population growth. It represents the carrying capacity, how the theoretical value of population that is possible with the current technology. But population itself tracks this through this series of, exponential growth phases or logistic growth spurts. And as we discussed earlier, as the hyperbola becomes very steep, the population growth can't keep up because this is limited to what human fertility can achieve. And the maximum growth rates we see typically of populations is 3%. The strongest growing populations are growing at about 3% per year. Sometimes they can hit, in very special circumstances, 10% per year, but certainly no more than that. And as this is tending towards infinity, even 10% growth rate per year is just not going to be able to keep up. So that's a finiteness effect, and explains why population is now lagging behind the curve. But in fact, we're not just seeing population sort of lagging behind and leaving the hyperbola. We're actually seeing a turnover and a tendency towards a certain limiting value. So this finiteness effect, would certainly seem to be true, but it doesn't explain that we're seeing, why it's actually plateauing. So in other words, although these finiteness effects certainly are true and certainly apply, it still seems there's some mileage to cover in terms of developing them into a full explanation of what's going on. And now, lastly, we'll consider the fact that population has stagnated before. As we saw, there was a transition in Roman times from an older hyperbola to a younger hyperbola, associated with a slowing down then of population growth that then took off again as the world transitioned from a fast-growing younger hyperbola that was heading towards a singularity around 100 BC to a slower-growing hyperbola that was heading towards a singularity around 2025. So with the fact that we've got a slowdown now, well, we've seen a slowdown in the past, and all these explanations for slowdown seem to be trying to explain something about the present, but something special about today that's causing a slowdown. But the fact that we've had a slowdown in the past, might be thought to suggest, well, none of these explanations really work because they assume or they rely on things that are special to today, but yet a slowdown occurred in the past when this didn't apply. So, maybe those aren't really good explanations for the slowdown. Maybe the slowdown is occurring for the same reasons it happened in the past, and we haven't yet understood what those are. So we haven't necessarily really explained today's slowdown. So I'll just say a few words on what people say about that, about the ancient versus the modern slowdown. So for Korotayev et al., as is seen, they have this theory in terms of literacy. So their explanation in terms of literacy applies to today, but not to the past slowdown. So they insist that today's slowdown is very different from slowdowns that have occurred in the past. They say that today's slowdown is a new phenomenon. Specifically, in the past, population slowdowns certainly occurred, but for things like plague, the Black Death, let's say, there was a population slowdown, the Black Death, or terrible wars, the 30 Years' War in Europe. These caused population slowdowns, and we can see them in the data, and they make sense. Of course, a deadly disease or a lethal war, it caused population to slow down. These are in fact Malthus's positive checks. So, we can see very clearly why those would cause population slowdowns. But today, the slowdown is occurring in times of relative peace and prosperity. Particularly, the slowdown has been occurring in the richest nations where, you know, life is easy. So there's some kind of negative checks going on. So all the past slowdowns were positive checks, but today's slowdown is different. It's relying on some kind of negative checks. I'll just put that in for completeness. So this is why they say it's a new phenomenon, and they're saying then it has a new explanation in terms of literacy. And looking particularly at the transition from the older hyperbola to the younger hyperbola, they say yes, this occurred for certain special reasons that applied at that time. One is higher populations forming a critical mass for new pathogens, new diseases. So the great growth of population that had been occurring thanks to the older hyperbola, and things like the Roman Empire building roads, connecting people, led to a large connected population that was sort of virgin territory for new diseases that then spread through them. And so the early centuries AD, the last few centuries of the Western Roman Empire, were characterized by high rates of epidemics. So they suggest that was one reason. Another reason is greater social complexity. So life in the Roman Empire was more complex for the individual than it had been centuries before, when they were, you know, just living in the countryside, quietly farming their territory, and not really bothered by big government. But by the time you had the Roman Empire, there was a lot of control of population, and they had new taxes to worry about. You know, the farmer now had to pay his dues to the emperor, and also new expectations. Life became richer. So, you know, what characterized the good life increased. People thought, you know, they needed more to be living well. The Roman statesman Seneca, in one of his letters, talks about how he visited the country estate of Scipio, who defeated the Carthaginians, and how he's looking around, just as today we might visit a stately home. He was looking around this old historic property that used to belong to Scipio, couple of centuries earlier. And he said the bathroom, he said it was so sparse. There was just one little window there and a tub, but sort of brick walls or stone walls. And he said no one would want to bath in a place like that. No one would want to have a bathroom like that today. Today we must have marble and heated water and fountains and so on to feel that we've got a decent bathroom. So people's expectations of what was a decent standard of living rose with the greater social complexity of the Roman Empire. And so this implied an increase in what in Korotayev and Co's equations we had as M, the minimum standard of living. It was economic output or economic production above that minimum standard of living, or economic production per capita above that minimum standard of living, that constituted the surplus that allowed population growth. So the greater social complexity of the Roman Empire raised this minimum. It gave people, you know, that because they had to meet these new taxes and they had these new expectations, they needed more money to be able to live. So the minimum standard of living increased. And so because the minimum standard of living increased, then the surplus decreased for the given income, the income that they had at that time. So in the past, that would have been a high surplus. But now, because of this sudden increase in the minimum standard of living, they now felt poorer. And this feeling of poorer meant that they had fewer children again, because it's part of the Korotayev model that it's the surplus that produces population growth. So that's another argument. And also they put it down to large empires, or large and powerful empires, reduced innovativeness. So they point out that at this time, around AD 1, the time that the transition was occurring from the older to the younger hyperbola, most of the world's population lived in a few large empires. In the west, the Roman Empire; in the east, the Han Chinese Empire; and in between, the Parthian and the Kushan empires. And these large, powerful empires were very controlling, and they suppressed innovations that were threatening to the social order. And we've seen this a lot through history. You know, the Ming emperor banned overseas sailing, saying, you know, it was frivolous. So he stopped the Chinese from exploring the world, and so reduced that innovation. The Ottoman emperor banned the printing press, as you know, because it could be used to print subversive material, and so the printing press didn't reach the Ottoman Empire till, you know, 300 years after it was already transforming Europe. So large, powerful empires reduced innovativeness, and this was a time when there were such large and powerful empires. So, so their argument is then that there are special reasons why slowdowns occurred before, but today's slowdown is different, and it's this literacy factor that explains it. But, you know, some people might say, well, I don't know if this is really true. Are things today really that distinctive? I mean, you know, yes, we may not be having some wars, but, you know, with COVID, for example, we've seen the possibility anyway of pathogens to reduce population today. You know, even if COVID itself wasn't, you know, quite the Black Death style event, it certainly shows that such things could occur. And, you know, people might wonder, well, is this really a time of prosperity? In fact, from the perspective of 2025, many people might feel that there's kind of austerity, and that they feel their standard of living is stagnating or even declining. So, you know, the people might not be persuaded so much by that. And, you know, today's governments are very powerful and very controlling again. So, you know, it's not really clear that this distinction is as stark as would be implied here. And in fact, one other thing I forgot to mention on this is they also point out that barbarians, if you like, as a shorthand, the barbarians were acquiring things like metal weapons, sophisticated metal weapons from the civilized areas, and then they were raiding it and invading it, and this also caused pressure on population and prevented population growth. But again, so you know, the barbarians invading attracted towards the rich, wealthy civilizations, and having acquired the technologies of the wealthy civilizations, the pressure they exerted slowed population down, and that's certainly true. You know, we know that barbarians came into the Roman Empire and transformed it. But yet again, people might say, well, yes, but you know, isn't this kind of happening again today, that people are coming towards the richer countries from the poorer ones and putting pressure on those populations and maybe affecting population growth? So again, you know, this is presented as something distinctive of the past that doesn't apply today. But you know, some people might say, well, you know, I'm not so sure that that is really a difference. And so this idea that the today's slowdown is very distinctive and requires a completely new explanation, maybe, but maybe not. And then Michael Golosowski, who I've mentioned a couple of times in connection, he's, you know, also written about these things. He says the literacy argument isn't really satisfactory because it can explain why population has stopped growing, because, you know, if particularly education causes women in particular to have fewer children, it can explain that, but it can't explain the slowdown of economic growth. Because as well as world population slowing, so is world GDP. In fact, in Korotayev's and Co.'s model, there's a connection between GDP growth and population growth. So, and you know, that holds up. So the world GDP is slowing down, but you would have thought that literacy would not have a negative effect on economic growth. You'd have thought that a more educated population would be more economically productive. So he's not really convinced that literacy per se explains the full dynamics of what is going on. And he suggests that what we really need, well, he says that the problem is that models based on differential equations, on calculus, can't really explain abrupt changes. Let's write that up. Differential equations are good at modelling continuous change, but they can't model things that happen all of a sudden. And yet what's happening today is something that is happening all of a sudden. We were on one trajectory and now suddenly we've moved into a different regime. And so we'll never explain that with differential equations, because they expect the system to behave in a particular way, not to shift from one mode of behavior to another. So his point is that we need the mathematics of critical transitions. He says that what we're looking at is a critical transition. And again, we discussed in the mathematics module the idea of critical transitions, things like disappearance of stable points and the idea of hysteresis. So we saw how in the mathematics of critical transitions we can show how as a system gradually changes, it goes past a critical point where a stable point of the system disappears. And so if the system was at this stable point, when that disappears, it suddenly must shift to some other stable point. And he's suggesting that that's what we're looking at today. There was a stable point of being in the hyperbolic growth, and then there's that stable point has disappeared, and we're now moving into a different regime of non-hyperbolic growth. And we need to think about it in terms of critical transitions. So, so the Korotayev et al. Model based on literacy, which we saw had 3 differential equations, he says this isn't going to work. What we need is a model that uses critical transitions, or the idea of critical transitions. And he says, as we just saw a little bit earlier, that one of the features of critical transitions is that of divergence, of correlation length. So this is in the example of the critical transition from ice to water, that at the critical transition, the sizes of patches becomes or has an infinite average. The average diverges. Above the critical point, when you've got just cold water, there are patches of ice still floating around in it, but those patches tend to have a definite average size. There aren't any huge ones. And below the critical transition, again, there's a definite size because it's basically just the whole contents of the beak or whatever is one lump of ice. The whole thing is ice below the critical point. But at the critical point, it's neither ice nor water. It's water with patches of ice floating in it, and those patches can be any arbitrary size, giving it a divergent, the average diverges. So the correlation length is, the size of the patch in this case. And he says that's what we're looking at on Earth today. So the couple of examples he gives of that is global trade, or let's say global market. So centuries ago, markets were quite localized. Each country was fairly self-contained market. Global trade was negligible. But today we live in a highly globalized world and a single global market. And so today's market really has no boundaries. It's become infinite, if you like. It's by occupying the whole Earth, it has no definite size. It never stops. It goes all the way round. So it has diverged. The size of the size of markets has diverged. They've all joined up now into one huge market with no boundaries. And another example is intercontinental ballistic missiles. So in the past, long ago in the Stone Age, your weapon was a rock, and you could throw a rock, and you could throw a rock so far, and then came along the technology of the spear, and you could throw that a bit further, and then came the bow and arrow, and you could throw that a bit further, and then the firearm, and you could shoot a bullet. But there was a finite limit to how far away you could kill someone. But now with intercontinental ballistic missiles, you can reach anywhere on the planet and kill anyone anywhere. So again, there's no boundary to how far our weapons can reach. They've effectively diverged to cover the whole planet. So he says these are examples of this divergence, the correlation length, which tells us we're looking at today a critical transition, and therefore why we need the mathematics of critical transitions. But while this is a reasonable argument, he doesn't really provide any mathematical details to how this would work. This is just a verbal argument, a critique, but not in itself a model that we can use. And so we've seen here some arguments as to why this slowdown is occurring. Kremer's idea that people's propensity to have children starts to decrease beyond a certain income. Korotayev et al.'s model in terms of literacy. Kapitsa's phenomenological model. Arguments about finiteness. And then this attempt to suggest whether today's slowdown is a new thing or is just the same old thing as we've had before, and the tendency is to argue it is a new thing. But we haven't necessarily come to any definite conclusion, because the thing is that nobody really knows. This is still perhaps an open research question. If we like the Korotayev et al. Literacy thesis, that's something to explore further and see if it really works. As I said, that Golosowski's got a critique of it here. I suggested that the turnover seems to be more abrupt than we're actually seeing in reality. So, there are things to question about it, see if we can maybe tweak that model to make it work better, what have you. My own preferred view is that we've seen, in fact, when we look close up at the changes of population through history, right back in the Stone Age, it's always been lumpy. It's always been a series of surges and plateaus, and it's just the envelope of that is this hyperbolic curve, and the innovations that have driven it have come in lumps, and then there's been a tendency to stabilize before the next great invention. And my preference is that we're not going through some special time, but this is just a typical time, and so this current stagnation is just the same as all the previous stagnations. It's just the way these things develop. It's kind of lumpy. If we look on a higher level of detail, it looks like a smooth curve, and we now seem to be deviating from it as we look close up at our own time. But in fact, if we look close up at any time, we'll see that it was going up in jumps. And these issues of finiteness certainly would seem to apply, because we can't perhaps increase too much beyond the present because of the finiteness of Earth's resources, and also particularly population can't grow at more than the 3% or maximum 10% rate that human populations can sustain. But those seeming finiteness limits may not be absolute limits, because we could imagine invention of artificial wombs, for example, that then remove that restraint. Reproduction will no longer be organic, so it won't be restrained by human physiology, and with artificial wombs we could reproduce at any rate we like, arguably. And similarly, we may not be constrained by the finiteness of the Earth if we can get into space and move on to other planets and eventually other stars and eventually other galaxies. And we've shown the ability to get into space already, so it's a very pessimistic attitude to suggest that will stop and human ingenuity won't be able to overcome it. Or at least I would say that's a very pessimistic attitude. Some people do believe there are definite limits. But this is an argument we can have. But this is my preferred view, that the present slowdown is just a typical slowdown that we have seen time and time again. But the kind of more common view in the literature is that the modern slowdown is a unique phenomenon, and it is kind of the final slowdown. So you take your pick as to which approach you find more convincing.